Alright, quick video on properties. This is really about how we measure waves, the properties of waves. And there's four criteria that we focus on. First is wavelength, next is frequency, wave velocity, and amplitude. And the symbols that you see on the side here, whether it's this Greek letter lambda, F, V, or M, this is what would show up in a as a letter in a formula. So if you see the Greek letter lambda in a formula, they're talking about wavelength. If you see the letter F in a formula, they're talking about frequency. So that just kind of is what these symbols on the side are. Now, the first of these four properties we're going to talk about is wavelength. And wavelength is really a measure of the distance from one cycle of a wave to the next cycle of a wave. If you remember, we talked about in class, if we look at this wave at the bottom here, that this is a cycle. It goes from the rest position up to the crest, down to the trough, and back to rest position again. That's a cycle. And then I have a second cycle here and a third cycle here. So if I measure the distance from like the crest of one cycle to the crest of the next cycle, that would be my wavelength. Or from the trough of one cycle to the trough of the next cycle, that would be the wavelength. Now this is using a transverse wave. You're not always looking at transverse waves. Sometimes you're looking at longitudinal waves where you don't have crests and troughs. So you would have to measure from compression to compression or from rarefaction to rarefaction. The unit we use to measure wavelength is the unit meters, and sometimes you'll have really tiny distances. So you might have very small numbers to deal with here. Now the next property to talk about is frequency. And frequency tells us the number of waves that are produced in a given amount of time. Really, it's the number of waves produced per second. And the unit we use is hertz. So 1 hertz is equivalent of 1 wave per second. So 10 hertz would be 10 waves per second. Now, as a wave's frequency increases, as you get a higher frequency, you get a shorter wavelength. There's an inverse relationship between these two variables. High frequency means short wavelength. So if you look at this wave here, we have a frequency right now of 1, 2, 3. And I can get that just by counting the number of crests or the number of troughs. So I have 3 hertz as my frequency. And my wavelength is maybe a medium length. But if my frequency was to increase to 6, I'd have a crest here, I'd have another crest here, another crest here, 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 here. I'd have twice the number of crests in the same amount of space. That means that my wavelength must be shorter. So having a shorter wavelength means having a higher frequency. That goes both ways. Now, the other thing that we know about frequency is how it relates to energy. And as frequency increases, you get more energy. So, if this has a frequency of 3 right now, if I had another wave with a frequency of 6 hertz, then my frequency of 6 hertz is going to be a wave that's carrying more energy. And again, the way we can figure out what our frequency is just by looking at a wave is to just count the number of crests or the number of troughs. Now that relies on the assumption that this entire wave here was produced in just 1 second, and we are going to go with that assumption. We're going to assume whatever pictures you're looking at of waves, that it was 1 second worth of time, unless you've been told otherwise. If the directions say that it was 3 seconds, then rely on that. But otherwise, if you're not told a given amount of time, assume that the wave was all produced in 1 second, which is why I can say this is 1, 2, 3 waves per second, because this whole thing was just 1 second. So far we've talked about 2 relationships and properties. The relationship between frequency and energy, which is direct, and the relationship between frequency and wavelength, which is inverse. If we look at these 2 different waves here, the wave on top has twice the frequency as the wave on the bottom. The wave on the bottom has a longer wavelength, though. It's actually twice the wavelength if everything was drawn properly. So the wave on top has a higher frequency and therefore has a greater amount of energy. That is a direct relationship. But we can also talk about wavelength as it relates to energy. If we know that the graph on top, the wave on top, has a higher frequency and more energy, and that it also has a lower wavelength, we can make the assumption, which we can go on and is accurate, that having a longer wavelength means having less energy. So high wavelength means a small amount of energy. So there is a inverse relationship between wavelength and energy. Long wavelength, low energy. It's just another relationship that we can recognize here between frequency and wavelength and their relationship to energy. Our next variable to talk about, or property to talk about, is the property speed. This is wave speed or wave velocity, and it tells us how quickly a wave travels through some medium. And it is dependent upon the medium. Some waves will travel quickly through one medium but slowly through another medium, or vice versa. The formula that we can use to calculate this is that wave velocity is equal to lambda, or wavelength, times frequency. And since wavelength is measured in meters and frequency is measured in seconds, we get distance, waves per second. We get this meters per second. Meters is our distance and seconds is our time portion for our wave velocity. Now, like I said, different waves will travel differently through various media. And if we think about some waves that we know require a medium, so the more dense the medium, like a solid has particles that are more densely packed together, is probably beneficial in terms of maximizing the speed of the wave. If a medium is required, you're probably going to travel more quickly. That wave is probably going to travel more quickly if the particles are closely packed together, like a solid. On the other hand, some waves don't require a medium at all. These waves are actually going to be slowed down by the particles. So the more tightly packed the particles are, the slower a wave would travel. So if we think about like waves that we know of, light waves are an example of an electromagnetic wave, a wave that does not require a medium. So the more densely packed the particles are, the slower that wave is going to travel. So as we get from, if we start with no medium at all in a vacuum, light is going to travel at its fastest speed, and it's going to travel progressively slower as we go from a vacuum to a gas, where the particles there's particles, but they're pretty spread apart. And then slower still when we get into a liquid, where there's particles and they're more closely packed than they were in a gas. And then slowest when we get into a solid, where the particles now become pretty tightly packed together. The opposite is the case of a sound wave, which is a longitudinal wave, a mechanical wave, that requires a medium in order to move. So a sound wave will travel more quickly through a tightly, densely packed medium like a solid, but more slowly through the medium as those particles become more spread out. So in a gas, the wave is going to travel more slowly. This is our formula when we put it into a triangle. We have wave velocity in meters per second at the top, with wavelength in meters and frequency in hertz down at the bottom. So you can use this triangle when we do some calculations. The last property to talk about is amplitude. And amplitude is the maximum distance that a wave vibrates away from its rest position. So it's the height that this wave flexes up to, or the depth that it drops down to get to the crest. Remember, the wave on its own, if it's just resting, if there's not a wave traveling through it, the medium is going to be right along rest position. So this tells us, the crest tells us how far up the particles were pushed, or the trough tells us how far down the particles were pushed. And that is our amplitude. Now, if we have a greater amplitude, then we have more energy. So there's a direct relationship between amplitude and energy. That is, amplitude increases, so does energy. Now, if I have two waves with identical amplitudes, the higher frequency is going to have more energy than a lower frequency wave. So frequency also has a direct relationship with energy. So we know that frequency has a direct relationship with energy. Amplitude has a direct relationship with energy. We also talked about wavelength and its relationship with energy, which is an inverse relationship. That is, wavelength increases, that the amount of energy in a wave decreases. So they all these things are related to each other. So you just quick checkup on stuff that you should have gotten down. Amplitude is measured in meters, and it is the distance. When we're talking about a transverse wave or even a surface wave, it's the distance from crest to rest position, or from trough to rest position. On a longitudinal wave, it's the amount that the particles move back and forth. It's how far they vibrate back and forth, or the amount of compression that can happen. Wavelength, which will show up as this Greek letter lambda, is measured in meters. In a transverse or surface wave, it's measured as crest to crest, or trough to trough. In a longitudinal wave, it would be compression to compression, or rarefaction to rarefaction. Frequency, which is measured in hertz, is the equivalent of the number of waves produced per second, where 1 wave per second is 1 hertz. And wave speed is the speed at which a wave travels through various medium, and it depends on the temperature of the medium and really the state of matter of the medium. Where some waves travel more quickly, the more densely packed the medium is, and other waves travel more slowly the more densely packed the medium is. So you have a chart like this on your page, and you should take a moment and fill this in. What you think the speed would be. Do you think things are going to be faster or slower through different medium or different media? And you have some terms to use that you can rely on to get this chart filled out. Get this filled out while you pause, and then start it back up, and we'll check out what the answers are. Alright, hopefully you paused and completed that chart. And so this is what the chart should look like when properly filled in. That light waves travel slowest through a solid. They're slow through a liquid, but not as slow. They get fast through a gas, and they're at fastest speed when they're traveling through a vacuum and there's no particles getting in their way. But sound waves travel the exact opposite. They can't travel at all through a medium. And then with a gas, the particles are pretty far apart. There's a lot of empty space between particles, so this caused the wave to travel kind of slow. In a liquid, the particles move a little closer together, so the energy can be transferred from particle to particle a little more quickly. And finally, when we have a solid where the particles are really tightly packed together, the sound wave can travel very quickly because, again, this energy needs to move from particle to particle. The particles are the machine through which the wave itself is transferred. So that is our video on our various properties for waves. If you haven't checked out the video on introduction to waves or on the basic nature of waves, you should do that now. And I will also post another video on the last section of our notes here, which is kind of the ways in which waves interact. So check out that video if you have not checked it out yet. All right, have a good one.